Welcome back to Physics 30. This is the last of the Unit 2 booklets. So taking a step away from friction and looking at universal gravitation. Okay, there's quite a few objectives that we'll look at for this booklet. So looking at field, force, mass, weight, and gravitational field strength. We'll look at the SI unit for force, mass, and weight. Identify important forces found in nature. Explain that force is a vector. Differentiate between mass and weight. Describe and compare mass, how they can be determined. Demonstrate an understanding of gravitational field. Describe why slight variations in gravitational field strength are found in different places on Earth. Compare the weight of a given object in different locations in space and on different celestial bodies. Solve problems involving gravitational force. Interpret the inverse square law and determine the gravitational force on an object at various distance. And lastly, 13, explain how the gravitational mass of an object with a known gravitational field can be derived. So first of all, 4 basic types of forces in nature: gravity, electric, weak nuclear, and strong nuclear. And for this one, of course, we're focusing on gravity. Gravitational field strength, we can think of that as being the amount of force exerted on a mass of 1 kilogram. So 1 kilogram object, what is the force involved there? That is the gravitational field strength. And we've touched on this already with Newton's second law. Newton's second law, F net equals ma, or if I rearrange that for A, it's F net over M, and one of the units, of course, we can see is newtons per kilogram, and of course that is equivalent to meters per second squared as well, if we do some manipulation with the force unit. So 9.8 meters per second squared, or 9.8 newtons per kilogram, we have the same thing, and you can see here how it changes into meters per second squared. So is 9.8 meters per second squared equivalent to that? Yes, it is. How does the acceleration due to gravity compare to the gravitational field strength? It's really 2 different ways of saying the same thing. So acceleration of gravity and gravitational field strength, as you can see, it's the same thing. So put a little box around that and maybe put a star. Mass represents the amount of matter in an object. So the amount of stuff that makes up an object itself, that is considered to be the mass. Does the mass of an object remain the same no matter where you are? Yes, it does, because the amount of stuff in you does not change. But weight is not the amount of stuff in you, it's the amount of gravity that's pulling down on you, the force of gravity pulling down on an object. And of course, that changes depending upon where you are. So the force of gravity that you experience on Earth is a lot more than the force of gravity on the moon, because the moon is a smaller object and it exerts way less gravity. What is so special about the distance of 9/10 away to the moon from the Earth? So here's the Earth, here's the moon. If you imagine yourself 9/10, this gives you an idea of the size of the gravitational field strength on Earth and moon, is that you would have an equal pull in either direction. So you'd have a weak force pulling towards Earth, the same force pulling towards the moon, and it is equal. So you'd have to be 9/10 of the way from the Earth to experience the same pull in either direction. So you'd experience weightlessness at that part. In which direction do gravitational forces act? So we kind of envision it, the center of the Earth or moon, wherever you are, the forces act to pull you towards the center of the planet. That's how we kind of envision it. All right. Next, we're kind of flying through this fairly quickly, so hopefully it's easy to understand. So of course, measuring weight, you can either use like a fish scale here. That's what this is supposed to be, a fish hanging from a scale, or of course your bathroom scales technically is measuring the force of gravity. If you were to take the scale to the moon, you would weigh slightly less, well actually quite a bit less. So it changes depending upon your location of Earth. Now the scale is calibrated in such a way that for the most part your mass and weight are the same on the within regions on the planet. But if you're to take it to the moon, it would weigh less. So to measure force of gravity, that's how we could do it. To measure your mass, what you'd have to do is have a setup like this. Now again, I mentioned this measures your mass a little because of how it's calibrated. But a balance scale like this, you could take anywhere in the universe and you would be able to measure your mass. So you're pulling on one end, and at the other side of the fulcrum, you have an equal mass pulling down in the other one. So it doesn't matter what the FG is, the FG will be similar. The amount of mass you have here to counterbalance your weight, that would be your mass. And of course, it doesn't matter if you're on the Earth or the moon. On the Earth, you'd have big FGs pulling down. On the moon, you'd have smaller FGs. But the idea is you'd have equal FGs pulling in opposite direction. Okay, Newton's law of gravitation. So it's similar to F net equals ma or Fg equals mg. But we're taking a look at the two masses involved. So we're looking at the attraction between two masses, the distance of their separation. Actually, it's the square of their distance of separation, and big G here, which really is a constant. So if we look here, if I look at it as a proportionality statement, F is directly related to mass 1 and mass 2, so the higher each mass is, the more force of gravity. But the further those objects are apart, the smaller the force gets. And it's an inverse squared law, as we'll see at the bottom on the next page here. We look at that. To make this an equal statement, we have to have some sort of constant value that doesn't change, and here's that constant number right here, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. So to make everything work off, we know that these are kilograms, meters squared, so those units will cancel and we'll be left with newtons for force. Now, to figure out that equation, Henry Cavendish, a scientist from many, many years ago, measured the force of gravity and was able to determine that constant. So measured the force of gravity between two spheres, right here, and was able to determine the value of G. Now I have a video to show you kind of a better explanation of that, since my drawing it really isn't the greatest here. So I will play that and we'll be able to see that.
Let me introduce you to chemist Henry Cavendish. How's it going, Henry?
Fine.
Henry is known for the Cavendish experiment. He was the first person to measure the force of gravity between masses in a laboratory and to produce an accurate value for the Earth's density.
Correct.
His work led to accurate values for the gravitational constant G. What's up, G?
Yo.
And the Earth's mass. The measurement of the gravitational constant allowed the mass of the Earth to be calculated for the first time. This also allowed the calculation of the masses of the Sun, the Moon, and the other planets. The first time this constant was used was in 1873, almost 100 years after the Cavendish experiment. Variations of Cavendish's results are still used today.
Indeed.
Now, for this experiment, he used a device with a torsion balance, like that, to measure the gravitational attraction between two 350-pound lead spheres and a pair of 2-inch 1.61-pound lead spheres. Using this experiment, Cavendish found that the Earth's average density is 5.48 times greater than that of water. It turns out that any two masses have a gravitational attraction for one another. If you put two bowling balls near each other, they will attract one another gravitationally. The attraction is extremely slight, but you could measure the attraction if you had the right equipment. From that measurement, you could determine the mass of the two bowling balls. The measurement of our planet's weight is derived from the gravitational attraction that the Earth has for objects near it. Cavendish performed his experiment in an outbuilding in the garden of his estate. For years afterward, his neighbors would point out the building and tell their children that this is where the world was weighed.
Okay, there we have it, folks. So as you can see, it looked something like this, and the idea was if we had this setup here, a very thin wire, and bringing two objects together. So we have a bowling ball here, bring it here, bowling ball on the opposite side, so this thing could technically spin. It would slightly attract, and we'd have a deflection in that light beam or laser beam, and from that he was able to mathematically figure out, well, you know what M1 is, you know what M2 is, you know the separation, and we could figure out the force and also this gravitational constant G. And once you know that, you can measure the force between any two objects at any separation. So it was a really important equation. If you look at one more thing here, describe the three important things to remember with the law of universal law of gravitation. So we're talking about equal and opposite forces here, so equal pulling forces. The proportion here, so if we look at the distance of separation here, I said I was going to mention this. If we look at, for example, if two objects become 5 times the distance from each other, you can see here that's 1 over 5 squared, 1/25th. So the force would be 1/25th as big. So it's an inverse squared. Whatever this changes to, it's inversely squared. That's what happens to the force. And the last thing here, that big value G is very small, and F are also very small too, unless we're dealing with extremely large objects. Okay, we'll stop it there, and I'll see you again at part 2.